An accurate and reliable means of measuring the outside air temperature is essential for the safe and efficient operation of the aircraft. Flight in icing conditions can be hazardous. Ice can form rapidly on an aircraft, especially in cloud, and ice buildup can result in a loss of lift, increased drag, and an increase in weight. In addition, a buildup of ice can inhibit the free movement of control surfaces, and damage can occur to the airframe as a result of ice being shed from propellers. Ice ingestion into a turbine engine can cause loss of power and even a flameout. And in piston-engined aircraft, carburetor icing can be a major cause of engine failure. Temperature also affects the density of the air, so it will have a direct bearing on aircraft performance, engine power, and the measurement of altitude and speed.
Measuring the outside air temperature, however, is not as straightforward as might at first be thought, because the movement of the aircraft through the air will cause the air temperature to rise in the immediate vicinity of the aircraft, as a result of friction, or kinetic heating, and air compression, or adiabatic heating. These terms are fully explained in the next lesson. This temperature will not be representative of the true outside air temperature.
It is the true outside air temperature that we need to know. So in this lesson we are going to look first at the basic types of air temperature thermometers in use and their principles of operation. Next, we will look at a typical total air temperature probe of the type used on modern high-speed aircraft. And finally in this lesson we will consider the errors which the instruments are subject to. Air temperature thermometers can be divided into two basic types: the direct reading thermometer and the remote reading thermometer. We will consider the direct reading thermometer first. One of the simplest is the bimetallic thermometer, and it works on the principle that two metals with different coefficients of expansion will expand at different rates if subjected to heat. If these two metals are bonded together to form a single bimetallic strip, the metal with the greater rate of expansion will cause the bimetallic strip to bend. How much the strip bends depends on the temperature rise and is therefore a measurement of temperature. The metals bonded together are often invar and brass.
Invar is a specially developed steel with a low coefficient of expansion. Brass, on the other hand, has a higher coefficient of expansion. If the bimetallic strip is now wound into a coil or helix and one end is held fast, then any temperature change will cause the helix to rotate. This rotation can be used to drive a pointer around a dial, which can be calibrated in the form of a temperature scale.
Simple direct reading thermometers are subject to a number of errors which we will look at later in the lesson, but they are adequate for use in relatively low-speed aircraft. It is often desirable to have temperature information in an electrical form, so that it can be fed to other instruments and systems. Remote temperature gauges work on the principle that the electrical resistance of certain materials changes with a change in temperature. Measurement of electrical resistance will therefore be a measurement of temperature. To measure electrical resistance, a resistance circuit is employed, commonly known as a Wheatstone bridge. We can see here a diagrammatic illustration of a Wheatstone bridge circuit. In basic form, the circuit consists of a power source and four resistors, labelled R1, R2, R3 and R4 in our diagram. For a given voltage input, the current flowing through the resistors will depend on the resistances. If the resistances are equal or balanced, the current flow in the circuit will be zero. If one of the resistors is exposed to the outside air as temperature changes, so will the resistance. This will cause an imbalance in the circuit and a current will flow, which will be proportional to the temperature change. The change in resistance is consequently a measurement of temperature change and can be calibrated. This is an accurate system which can detect even small changes in temperature, and as the system works on the principle of balancing resistances, any fluctuation in the circuit voltage will not affect the accuracy of the system. Let us now look at a typical total air temperature probe of the type used on a modern high-speed aircraft. The probe is usually constructed from nickel-plated beryllium copper, which provides good thermal conductivity and strength. This type of probe consists of an air intake mounted at right angles to a small hollow strut or casing. Inside the casing is a pure platinum wire resistance sensor. Platinum is used because it has a very high rate of conductivity and gives a rapid response to temperature change. Platinum also has a linear resistance change to temperature change relationship, which makes it ideal for temperature measurement. The probe is fixed to the fuselage in a location which minimizes any boundary layer effect, usually the front fuselage. Boundary layer effect is discussed in detail within aerodynamic courses on principles of flight. Here we can see a diagrammatic cross-section of a total air temperature probe. Let us look at how it works. It can be seen that some of the air entering the probe is turned at right angles to pass over the sensing element. This is to separate the air to be sensed from any water or solid particles present. Flow separation is achieved because water or solid particles have sufficient kinetic energy to pass directly through the air intake and exit. The bleed holes we can see in the intake casing allow the higher pressure air escaping from within the intake casing to draw off boundary layer air. An integral heating element prevents the formation of ice. The effect of the heating element on the temperature sensed is small and is not significant. It is also necessary to measure air temperature on the ground. A factor affecting takeoff distance and the takeoff power required is temperature. A reduced power takeoff may therefore be possible, and this is a valuable operational consideration. Without forward movement of the aircraft, air within the sensor casing can stagnate. Stagnated air could give a false indication of the outside air temperature. To re-establish an outside air flow within the probe, an air-to-air ejector or aspirator is used. The principle we can see in operation here is that pressurized bleed air is being drawn from a compressor stage of a running engine or auxiliary power unit and is being fed through the aspirator. This creates a negative pressure differential within the sensor casing, which draws fresh outside air past the sensor element.
Finally, in this lesson, we will look at the errors which air temperature gauges are subject to.
The first is instrument error. This occurs in the manufacturing process, and unfortunately, manufacturing imperfections are difficult to avoid. The second error is
environmental error. This error can occur as a result of solar heating of the temperature sensor. Direct reading thermometers in particular can be vulnerable to this type of error. Solar heating can be reduced by shading, which happens in a remote detector. Icing is also an environmental error.
And thirdly, we have heating error. We will recall from earlier in the lesson that the movement of the aircraft through the air will cause the air temperature to rise in the immediate vicinity of the aircraft. The rise in temperature is caused by friction or air compression as the aircraft moves through the air, and it accounts for by far the greatest error in high-speed aircraft. Low-speed aircraft are less affected by friction or air compression and are therefore less vulnerable to this type of error. In this lesson, we have considered why accurate air temperature measurement is necessary and the problems associated with air temperature measurement. We should also now be familiar with the principles of operation involved in a direct reading thermometer, a remote reading thermometer, a total air temperature probe, and an aspirated total air temperature probe. This ends our consideration of air temperature sensors. Part 2 of air temperature measurement will take us through the relationship between temperature and speed and define static air temperature, total air temperature, and RAM air temperature. It will also look at methods of air temperature correction. A summary of the main points of the lesson follows. Temperature affects aircraft performance. Ice can build up quickly, especially in cloud. Ice build-up can cause loss of lift and an increase in drag and weight. Temperature affects air density, which affects engine power and the measurement of altitude and speed. Kinetic and adiabatic heating will give a false indication of the true outside air temperature. The two basic types of air temperature thermometers are the direct reading and the remote reading thermometer. The bimetallic thermometer works on the principle of two metals bonded together with different coefficients of expansion will expand at different rates. The two metals often used in the bimetallic thermometer are invar and brass. The remote reading thermometer works on a Wheatstone bridge principle. The total air temperature probe is usually constructed from nickel-plated beryllium copper. In the total air temperature probe, the sensing element is usually made of pure platinum. The total air temperature probe is fixed to the aircraft in a location which minimizes the boundary layer effect. In the total air temperature probe, an integral heating element prevents the formation of ice. An aspirated total air temperature probe uses bleed air to create an ambient airflow through the probe while the aircraft is stationary. Air temperature gauges are subject to instrument error, environmental error, and heating error.
In the last lesson, we looked at the two types of basic design of air temperature measurement devices. These were the direct reading type and the remote reading thermometer. Both types are subject to the three errors of all air temperature measurement instruments, which are instrument error, environmental error, and heating error. Heating error is caused by the movement of the aircraft through the air. The air temperature rises in the immediate vicinity of the aircraft as a result of friction or kinetic heating, and air compression or adiabatic heating. Kinetic heating is the main contributor to the temperature rise effect in the direct reading thermometer. As the speed increases, more and more molecules of air per second impact against the flat plate at the front of the probe. This causes a temperature rise due to friction. Adiabatic heating is the main contributor to the temperature rise effect in the remote reading, or total head, thermometer. It is caused by a conversion of energy, not a direct application of heat. For example, boiling a kettle is a direct application of heat, whereas pumping a bicycle pump causes a rise in temperature without any input of heat because pressure energy is converted into temperature energy. In the remote reading temperature probe, the outside airflow, which may be several hundred knots, is brought virtually to rest in the platinum measurement chamber very rapidly. The energy of the moving air is released in the form of a temperature rise. This is adiabatic heating. Let's show these combined effects on a graph. The y-axis represents temperature, and the x-axis represents the aircraft's speed. The temperature of the undisturbed air through which the aircraft is about to fly is what we are trying to measure. We call this the static air temperature, or SAT for short. In formulae, it is often written as T subscript S. However, the effect of the heating error is to cause too high a temperature to be measured, If there were no losses in the measurement process, we would measure total air temperature, otherwise called TAT. The difference between static air temperature and total air temperature is called total ram rise. There is a known relationship between the relative speed and the temperature rise. The laws of thermodynamics are such that the combination of kinetic and adiabatic heating will always add up to total ram rise. Total air temperature is defined as the maximum temperature attainable by the air when brought to rest adiabatically. And in formulae it is often written as T subscript T. Unfortunately, any measurement process always has leaks and inefficiencies, so we do not measure the full ram rise. The amount of ram rise actually sensed is called the measured ram rise. If we could measure the total ram rise, we would measure the total air temperature. However, in practice, what we measure is the ram air temperature, which is lower. The ratio of the measured ram rise to the total ram rise is called the recovery factor. Suppose that, because of losses and inefficiencies in measurement, the measured ram rise is only 90% of the total ram rise. In this case, the recovery factor would be 0.9 or 90%. In formulae, the recovery factor is often written as K or K subscript R. Let's see how these definitions interact. We'll assume an aircraft experiencing a static air temperature of -60 degrees Celsius at a speed where the theoretical total ram rise would be plus 13 degrees. Assume a recovery factor of 0.9. The static air temperature is -60 Celsius. The total ram rise is plus 30 degrees. Remember, this is a theoretical figure and cannot actually be achieved. The total air temperature would therefore be -30 degrees Celsius. The recovery factor is 90%, which is expressed as 0.9. Therefore, the measured ram rise is total ram rise times 0.9, which is plus 27 degrees. Applying plus 27 to -60 gives us a ram air temperature of -33 degrees Celsius. This is the figure which you would actually see on the ram air temperature gauges. You would then use one of several methods to arrive at your correction factor of -27 degrees and then apply it to get the static air temperature, which is what you want. Theoretically, uncorrected air temperature gauges give ram air temperature, not total air temperature. However, in many aircraft, the gauge is incorrectly labelled TAT. What you see on the gauge is sometimes called indicated outside air temperature, or IOAT. Static air temperature is sometimes called corrected outside air temperature, or COAT. OAT on its own stands for outside air temperature and is usually taken to mean SAT. The relationship between them is that total air temperature equals static air temperature plus ram rise. Static air temperature is always colder because total air temperature has undergone heating and so ram rise is always positive. Or indicated outside air temperature equals corrected outside air temperatures plus ram rise. The indicated temperature can be converted to static air temperature by the following methods. The rapid formula for practical use in the air. The navigation computer. The accurate formula which you will need for exams. Data tables. And the air data computer. There is a rapid formula for use in the air. It is simply that the ram rise equals your true airspeed in knots divided by 100, all squared. So that if your TAS is 200 knots, the ram rise is 4 degrees. And if your TAS is 300, the ram rise is 9 degrees. And so on. This formula should not be used in exams because it is not quite as accurate as the computer solution. But it is good enough for practical use in the air when a quick solution is required and it is not convenient to find a nav computer or look up tables. The nav computer is the recommended way to find ram rise in exams and is used in multi-crew aircraft if no air data computer is fitted. On the slide rule face of the nav computer there is a blue scale. The outer scale is true airspeed, and the inner scale is ram rise. If the TAS is 400 knots, the ram rise is plus 17 degrees. The accurate formula may be the only way of solving some exam questions. It is also the basis on which the navigation computer, the tables and the air data computer solutions are calculated. The formula is that static air temperature equals the total air temperature divided by 1 plus 0.2 times Kr times the Mach number squared. In the context of this equation, TAT is actually RAT, as is often the case. This is the temperature that you see on the gauge. Kr is the recovery factor. On most modern aircraft, it is usually very close to 1. Mach number will be explained in a later lesson. It is a measure of your speed compared against the speed of sound and is indicated on an instrument called a Mach meter. Before we continue with the worked example, we need to explain that both SAT and TAT in this equation are in degrees absolute, or Kelvin. When Celsius designed his temperature scale, he chose the boiling point of water as 100 degrees Celsius and the freezing point of water as 0 degrees Celsius. This seemed reasonable, given the state of physics at the time. However, the problem with normal Celsius temperature scale is that it changes sign at 0 degrees Celsius, the freezing point of water. Numbers above 0 are positive, whilst numbers below are negative. But to measure the relative levels of hotness in objects in a meaningful way, we should start from a baseline of absolute 0, no heat at all. This occurs at minus 273 degrees Celsius on the Celsius scale. So, minus 273 degrees Celsius is 0 degrees A or 0 K on the Kelvin scale. 1 Kelvin, or 1 degree absolute, is the same amount of temperature change as 1 degree Celsius. Therefore, the freezing point of water occurs at 273 K, the boiling point of water at 373 K, and so on. Now, let's try a worked example. You are in a Boeing 737 and your indicated TAT is minus 20 degrees Celsius. The Mach number is 0.73, which is a typical speed for a Boeing 737 in long-range cruise mode. The recovery factor is 0.98, which is a typical value for a modern TAT probe. The value for Kr, the recovery factor, is determined by flight testing and is published in the operating instructions for the aircraft. The TAT is minus 20 degrees Celsius. This is the same as 253 kelvins, or 253 degrees absolute. Now we substitute into the formula. The TAT is 253. KR is 0.98. The Mach number is 0.73. If you get your calculator out and do the sums, you'll find that this works out as 253 divided by 1.1044, which is 229. So the static air temperature is 229 kelvins, or degrees absolute. This is the same as minus 44 degrees Celsius. So we have used this formula to go from a total air temperature of minus 20 to a static air temperature of minus 44. This has shown you how to use the equation, which you need to know for the exam. However, airline pilots do not really do these sorts of calculations in flight. In practice, in older aircraft, they would use tables. And in newer aircraft, the air data computer would do it for them. This is an example of the correction table for the Boeing 737. Again, we'll show how it works and we'll use the same numbers. You enter with the left-hand column and go down to the indicated total air temperature, which is minus 20 in our example. Then, in the Mach number row, you find 0.73. You read off the static air temperature where the row and column meet. As we can see, it gives the same answer, minus 44. However, any large airliner less than 20 years old or thereabouts will have an air data computer. We will look at this device in more detail in a later lesson. The ADC is a computer that takes inputs of Pitot-static, angle of attack and TAT and processes them to calculate airspeeds, altitude, Mach number, TAT and SAT. The static air temperature is therefore automatically computed. The majority of the aviation world uses centigrade or Celsius as a temperature scale, but Fahrenheit is still widely used in the USA. There are 9 degrees of Fahrenheit temperature rise to 5 degrees of the equivalent Celsius rise. And 0 on the Celsius scale is plus 32 Fahrenheit on the Fahrenheit scale. There are formulae for conversion, but for simplicity, use the temperature conversion scale on the CRP5. Let's summarize what we've covered. Heating error is caused by the movement of the aircraft through the air. Kinetic heating is the main contributor to the temperature rise effect in the direct reading thermometer. Adiabatic heating is the main contributor to the temperature rise effect in the remote reading, or total head, thermometer. The static air temperature is the temperature of the undisturbed air through which the aircraft is about to fly. This is what we are trying to measure. The heating effect would give us total air temperature if the measurement process were 100% efficient. The difference between the static air temperature and total air temperature is called total ram rise. The laws of thermodynamics are such that the combination of kinetic and adiabatic heating will always add up to the total ram rise. However, because of measurement inefficiencies, the measured ram rise is less than the total ram rise. What we see on the gauge is the ram air temperature. The ratio between the measured ram rise and the total ram rise is called the recovery factor. The indicated temperature can be converted to static air temperature by the following methods. The simple formula should only be used in the air. It is not accurate enough for exams. The nav computer is the recommended way to find RAM rise in exams and is used in multi-crew aircraft if no air data computer is fitted. The accurate formula may be the only way of solving some exam questions. It is also the basis on which the navigation computer, the tables and the air data computer solutions are calculated. It uses the Kelvin or absolute scale. In practice, tables are used on older aircraft. And the air data computer gives a direct readout of static air temperature on more modern aircraft. If you have to convert Fahrenheit to centigrade, use the navigation computer. This concludes the lessons on temperature measurement. The next lesson will go on to consider the air pressure instruments. In this lesson, we are going to look at pressure heads and the pressure instruments they serve. In order to understand the function of pressure heads, we first need to define static, dynamic and pitot pressures and identify the flight instruments which use these pressures. So let us start with the definition of static pressure. Static pressure is the pressure felt on an aircraft as a result of being in the Earth's atmosphere. It is present when the aircraft is not moving. Static pressure is felt equally all over the aircraft. If the aircraft now moves forward through the air, the leading surfaces of the aircraft will experience an additional air pressure or impact pressure, and this is known as dynamic pressure. The full dynamic or impact pressure will be experienced when the airflow is brought to rest against the moving aircraft. So we can say, in basic terms, that dynamic pressure is the force the air exerts when brought to a standstill against a moving body. The leading surfaces of the aircraft will therefore be subjected to the combination of static pressure plus dynamic pressure, and this total pressure is known as Pitot pressure. The word Pitot is named after the French physicist who invented a method of measuring total pressure. We can see, therefore, that to find dynamic pressure we simply have to subtract static pressure from Pitot pressure. The basic flight instruments which use static pressure only are the altimeter, shown here, and the vertical speed indicator, or VSI, shown here. Both these instruments are dealt with in detail in their own specific lessons. The basic flight instruments which use both static and Pitot pressure are the airspeed indicator, or ASI, shown here, and the Mach meter, shown here. Again, both these instruments are covered in detail in their own specific lessons. Pitot and static pressure inputs are also required for an air data computer or an ADC. This will be dealt with in detail in the lesson on air data computers. Note that pressure instruments suffer from what is known as instrument error. Instrument error is basically due to mechanical imperfections, but this will be dealt with in the lessons on each instrument. Let us now look at pressure heads. Pressure heads are probes fixed outside the aircraft and which form part of Pitot and static pressure sensing systems. Pitot pressure is sensed by a pressure head known as a pitot tube, and we can see here that a pitot tube is simply an open-ended tube which faces forward into the airflow. It must be positioned outside the boundary layer, which is air close to the aircraft which exhibits properties which could interfere with the accuracy of the pitot measurement. A pitot tube usually consists of a head on a strut or a tube on the nose. It is fixed parallel to the longitudinal axis of the aircraft to ensure that the full dynamic pressure is sensed. The air can either be brought to rest inside the pitot tube against a stagnation wall, which is simply a pressure measuring flat surface, and then transmitted up the pitot pipelines to the user instruments, or it can be passed directly up the pitot pipelines. A static head is a perforated tube with its forward end sealed against the airflow. The perforations along its length allow only static air pressure to enter the static pressure sensing system. It is also fixed parallel to the longitudinal axis of the aircraft to reduce the possibility of dynamic air pressure entering the static air sensing system. The pitot and static heads may be combined into a single pressure head, known as a pitot-static head, which we can see in this example. Here we have the static tube surrounding the pitot tube. The systems are still separate, and each system has its own pressure line leading to its own pressure instruments. A heating element is incorporated to prevent the formation of ice. The heating will affect the density of the air, so this must be suitably calibrated out. Any water entering the system is discharged through drain holes. Some air pressure will escape through the drain holes, but this is also suitably calibrated and allowed for in the design. To summarize then, static pressure is the ambient air pressure experienced by an aircraft because it is in the Earth's atmosphere. Dynamic pressure is the force the air exerts when brought to rest against a moving body. Pitot pressure is the combined or total pressure of dynamic and static pressures. The basic flight instruments which use static pressure are the altimeter and the vertical speed indicator, or VSI. The basic flight instruments which use pitot and static pressure are the airspeed indicator, or ASI, and the Mach meter. Pressure heads form part of separate pitot and static pressure sensing systems. The separate pressure heads may be combined into a single pitot-static head. A heating element will be incorporated into a pressure head to prevent the formation of ice.
In this lesson, we are going to look at the principle of operation of the pressure altimeter and how the pressure altimeter is calibrated. We will also look at the simple altimeter, the sensitive altimeter, and the servo-assisted altimeter. The pressure altimeter can be thought of as a pressure gauge, which senses change in static air pressure and, by means of calibration, expresses the change of static air pressure as a change in altitude. So in order to appreciate how the altimeter works, we first have to look at the atmosphere and how altitude affects static air pressure. In the atmosphere which surrounds the Earth, the static air pressure experienced at any point will depend on the weight of the air above that point. If we imagine a column of air extending vertically upwards from the Earth's surface to the outer limits of the atmosphere, it will be clear that the higher up the column we climb, the shorter the column of air above us becomes, and so the weight of air above us reduces. In other words, the greater the height, the lower the pressure. By measuring pressure, the altimeter measures height or altitude. Unfortunately, the relationship between pressure and altitude is not linear. Additionally, high and low pressure weather systems can produce significant air pressure changes for any given altitude. If we look at the isobar chart shown here, we can see that if we were to travel from the UK to Iceland at mean sea level, the air pressure above us will change from around 1036 millibars or hectopascals to approximately 996 millibars or hectopascals. The matter is further complicated because the rate at which temperature changes within the air will vary considerably, and this affects the air pressure also. With all these variables in the atmosphere, calibration of the altimeter is a complex matter, and it is necessary to assume an average or standard atmospheric condition from which to apply any necessary corrections. The atmospheric condition universally adopted as standard is known as the International Standard Atmosphere, or ISA. ISA conditions assume the following. Firstly, that mean sea level pressure is 1013.25 millibars or hectopascals, and the temperature is plus 15 degrees Celsius, while the air density is 1,225 grams per cubic meter. Secondly, that from mean sea level up to 36,090 feet, or 11 kilometers, temperature is assumed to reduce by 1.98 degrees Celsius per 1,000 feet, or 6.5 degrees Celsius per kilometer. Thirdly, that from 36,090 feet, or 11 kilometers, up to 65,617 feet, or 20 kilometers, the temperature is constant at minus 56.5 degrees Celsius. And finally, from 65,617 feet, or 20 kilometers, up to 104,987 feet, or 32 kilometers, temperature increases by 0.3 degrees Celsius per 1,000 feet, or 1 degree Celsius per kilometer. On the basis of these assumptions, the pressure which corresponds to any given altitude in the ISA can be calculated, and under laboratory conditions, any altimeter readout can be checked against the ISA calculated figures. Any discrepancies within accepted limits can be listed as instrument error over the operating range of the altimeter, and can be recorded on a correction table for the altimeter. Before we move on to looking at how the altimeter works, something that will be apparent if we think about it is that if the altimeter is calibrated to ISA conditions, the altimeter can only indicate the correct altitude where ISA conditions exist. And as we have seen, atmospheric conditions vary considerably. The lesson on altimeter pressure settings deals with how we overcome this problem. Let's look at how the altimeter works then. In its simplest form, static pressure is fed into a sealed instrument case from the static source. Inside the instrument case is a partially evacuated capsule, or aneroid capsule. Expansion and contraction of the capsule is kept under control by a leaf spring, and the controlled movement is transmitted via a system of linkages to the pointer on the instrument dial. As altitude increases, the static pressure inside the instrument case decreases. The capsule expands, which causes the pointer to rotate and indicate an increase in altitude. In the descent, the capsule is compressed, and the pointer moves in the opposite direction. The linkage incorporates a temperature compensating device to minimize errors caused by expansion and contraction of the linkage and changes in spring tension due to changes in the temperature of the mechanism. We can see the principle of the linkage mechanism in operation, although the actual arrangement is much more complex. The simple altimeter has a manual setting knob which is geared to the pointer. If this knob is used to set 0 on the ground, we call the altimeter setting QFE, and we say that the altimeter indicates height. These terms will be explained in more detail in the next lesson. If we set the airfield distance above sea level when on the ground, we call the pressure setting QNH, and the altimeter indicates altitude. Again, we'll explain this in more detail later. The sensitive altimeter uses essentially the same principle of operation as the simple altimeter, but incorporates some additional refinements. The single aneroid capsule of the simple altimeter is replaced with a bank of 2 or sometimes 3 aneroid capsules. We can see 2 capsules represented diagrammatically here. The combination of capsules gives increased movement for changes in pressure, and this makes the instrument more sensitive to small changes in altitude. Accuracy is also improved by the use of jeweled bearings in the mechanical linkages, which reduces friction. As with the simple altimeter, a temperature compensating device is incorporated, which minimizes the errors caused by expansion and contraction in the linkages. Some sensitive altimeters incorporate vibrators, which help overcome friction and the inertia of the mechanical linkages. This assists in giving a faster response rate to altitude change. Looking at the sensitive altimeters illustrated on the screen, we can see that the more sophisticated mechanism of the sensitive altimeter enables the use of 3 pointers on the instrument dial. 1 pointer for tens of thousands of feet, 1 for thousands, and 1 for hundreds of feet. While this may initially be seen as advantageous, there is a major shortcoming here, in that the 3-pointer system is easy to misread. Both the altimeters shown here are actually indicating 24,100 feet. If we look at the sensitive altimeter to the far right now, we can see that in this version of the instrument, a much clearer display is achieved by substituting 2 of the 3 pointers with a digital altitude readout. A single pointer is retained to indicate 1,000 feet per revolution, and to provide a valuable indication of the rate of altitude change. This altimeter is also indicating 24,100 feet. The sensitive altimeter also incorporates a variable subscale, which can be manually controlled to set a required pressure datum. The relevance of this facility is discussed in the lesson on altimeter pressure settings. But let's take this opportunity to see how changing the altimeter subscale changes the indicated altitude. A further refinement of the pressure altimeter is the servo-assisted altimeter, which gives improved accuracy, particularly at high altitudes, where the change in air pressure is much smaller than at low altitudes for a given change in height. The principle of the servo-assisted altimeter is that direct mechanical linkage between the aneroid capsules and the pointer is replaced with an electromagnetic system. Minute movements of the capsules can be sensed by this system, and the movements converted into electrical current by an electromagnetic pickoff. The electric current generated is amplified and used to drive a servo motor which rotates the pointer. We can see here in diagrammatic form how this is achieved. Movement of the capsules is transmitted to a pivoted bar, known as an I-bar. Opposite the I-bar is an E-shaped bar. As we can see, the E-bar has coils wound around each leg. The coils on the outer legs are wound in opposite directions, which causes them to be 180 degrees out of phase with each other. AC current is fed to the middle leg, which sets up an alternating magnetic field in the outer legs. Because the windings on the outer legs are 180 degrees out of phase with each other, when the gap between the I-bar and the legs of the E-bar is equidistant, the magnetic fields generated are equal and opposite and cancel each other out. No current will therefore flow in the circuit. When the capsules expand or contract with changes in altitude, they move the I-bar on its pivot, and the gap between the I-bar and E-bar will change This causes an imbalance in the magnetic fields, and an electrical current will flow in the circuit. The current is amplified and fed to the servo motor, which drives the pointer. A worm drive and cam mechanism realigns the I bar with the E bar. Once realigned, equilibrium is restored, and the altimeter indicates the correct altitude. In practice, the E bar movement and the realignment can be considered to be a single continuous process. To recap then, we can say that the advantage of the servo-assisted altimeter are that it gives improved accuracy, particularly at higher altitudes. Additional advantages are that friction and manufacturing imperfections in the mechanical gearing of a conventional altimeter are reduced, and altitude sensing in electrical form is available as a central source of information for digital readouts and systems, such as autopilot, flight data recorder, and altitude warnings. This concludes the lesson. A summary of the main points to consider from the lesson follows. The pressure altimeter senses change in static pressure, and by means of calibration expresses the change in static air pressure as a change in altitude. The greater the altitude, the lower the air pressure. High and low pressure weather systems produce air pressure changes at any altitude. An adopted standard atmospheric condition is required in order to calibrate the altimeter. The standard atmospheric pressure is the International Standard Atmosphere, ISA. The pressure altimeter consists of a sealed instrument case with a partially evacuated capsule or aneroid capsule inside. Static pressure is fed to the instrument case. As altitude increases, the static pressure decreases, and the aneroid capsule expands, causing a pointer on the altimeter dial to show an increase in altitude. The converse applies in the descent. The simple altimeter incorporates a manual pressure setting knob and a temperature compensating device in the linkages. The sensitive altimeter incorporates 2 or 3 aneroid capsules to increase sensitivity to small changes in altitude. In the sensitive altimeter, jeweled bearings are incorporated to reduce friction. In the sensitive altimeter, vibrators can be incorporated to overcome friction and the inertia of mechanical linkages. The sensitive altimeter allows the use of a 3-pointer dial. However, it is easy to misread. The servo-assisted altimeter gives more rapid response and improved accuracy, particularly at high altitudes. The servo-assisted altimeter replaces mechanical linkages with an electromagnetic E and I bar system.